Good morning, sir. Good morning, classmate. I'm Chasa Capasio, and today I will be discussing the Chinese and Indian mathematics. Let us start in the Chinese number system. The simple but efficient ancient Chinese numbering system, which dates back to at least the second millennium BCE, used small bamboo rods arranged to represent the numbers 1 to 9, which were the places in columns representing units, tens, hundreds, thousands, etc. Therefore, a decimal place value system, it was adopted in the West and it made even quite complex calculations very quick and easy. The use of the abacus is often thought as a Chinese idea, although some type of abacus was in use in Mesopotamia, Egypt, and Greece, probably much earlier than in China. The first Chinese abacus or swanpan, Chinese abacus in 2nd century BCE. So this is the ancient Chinese number system, that is the bamboo rods. And now, let us proceed to Lushu Magic Square. Was a pervasive fascination with numbers and mathematical patterns in ancient China, and different numbers were believed to have cosmic significance, in particular the magic squares. Squares of number which each row, column, and diagonal added up to the same total were regarded as having great spiritual and religious significance. The Lucius square, an order 3 square which each row, column, and diagonal adds up to 15. It perhaps the earliest of this, dating back to around 650 BCE. The legend of Emperor Yu's discovery of the square on the back of a turtle is a set taking place in about 2800 BCE. So this is the Lushu Magic Square with its traditional graphical representation. In the 13th century, Yang Hui also produced a triangular representation of binomial coefficients identical to the later Pascal's triangle, and was perhaps the first to use decimal fractions in modern form. Yang Hui happens to be a reputable figure, one who was known for his remarkable contributions in the field of mathematics. He was a great Chinese mathematician and writer. He served through his inventions during the Song Dynasty in China. This is Yang Hui, a noble Chinese mathematician. And now, let us proceed in the early Chinese method of solving equations. So this is the sample problem. If 1 plum and 3 peaches weigh a total of 750 grams and 2 plums and 1 peach weigh a total of 500 grams, how much does a single peach and plum weigh? First, 750 grams plus 750 grams equals 1,500 grams. So 1,500 grams minus 500 grams equals 1,000 grams. Then 500 grams minus 200 grams equals 300 grams. A textbook called Ju Chang Xuanshu, or 9 Chapters on the Mathematical Art, written over a period of time from about 200 BCE onwards, probably by a variety of authors, became an important tool in the education of such a civil service, covering hundreds of problems in practical areas such as trade, taxation, engineering, and the payment of wages. It was particularly important as a guide to how to solve equations, the deduction of an unknown number from other known information using a sophisticated matrix-based method which did not appear in the West until Carl Friedrich Gauss rediscovered it at the beginning of the 19th century, and which is now known as Gaussian elimination. Johann Carl Friedrich Gauss is sometimes referred to as the Prince of Mathematicians and the great mathematician since antiquity. He had a remarkable influence in many fields of mathematics and science, and is ranked as one of history's most influential mathematicians. Among the greatest mathematicians of ancient China was Liu Hui, who produced a detailed commentary on the 9 chapters in 263 CE or current era, was one of the first mathematicians known to leave roots unevaluated, giving more exact results instead of approximations. By an approximation using a regular polygon with 192 sides, we also formulated an algorithm which calculated the value of pi as 3.14159, correct to 5 decimal places, as well as developing a very early form of both integral and differential calculus. And in this picture, this is the Chinese remainder theorem. The Chinese went on to solve far more complex equations using far larger numbers than those outlined in the 9 chapters. They also started to pursue more abstract mathematical problems, although usually couched in rather artificial practical terms, including what has become known as the Chinese remainder theorem. By the 13th century, the golden age of Chinese mathematics, there were over 30 prestigious mathematics schools scattered across China. Perhaps the most brilliant Chinese mathematician of this time was Qin Jushao, a rather violent and corrupt imperial administrator and warrior, who explored solutions to quadratic and even cubic equations using a method of repeated approximations very similar to that later devised in the West by Sir Isaac Newton in 7th century. This is Isaac Newton, was an English mathematician, physicist, astronomer, alchemist, theologian, and author who was described in his time as the natural philosopher. So Qin extended his technique to solve albeit approximately equations involving numbers up to the power of 10, extraordinary complex mathematics of its time. And now, let us proceed in Indian mathematics. So, this picture is the evolution of Hindu-Arabic numerals. Despite developing quite independently of Chinese and probably also of Babylonian mathematics, some very advanced mathematical discoveries were made at a very early time in India. Mantras from the early Vedic period before 100 BCE invoke powers of 10 from 100 all the way up to a trillion, and provide evidence of the use of arithmetic operations such as addition, subtraction, multiplication, fractions, squares, cubes, and roots. As early as the 8th century BCE, long before Pythagoras, a text known as the Solva Sutras or Solva Sutras listed several simple Pythagorean triples as well as a statement of the simplified Pythagorean theorem for the sides of a square and for a rectangle. Indeed, it seems quite likely that Pythagoras learned his basic geometry from the Solva Sutras. The sutras also contain geometric solutions of linear and quadratic equations in the single unknown, and give a remarkable accurate figure for the square root of 2. As early as the 3rd or 2nd century BCE, Jain mathematics recognized 5 different types of infinities. First is the infinite in one direction, second in two directions, third in area, fourth is infinite everywhere, and lastly perpetually infinite. Ancient Buddhist literature also demonstrates a present awareness of indeterminate and infinite numbers, deemed to be 3 types. First is countable, uncountable, and infinite. Like the Chinese, the Indians early discovered the benefits of a decimal place value number system, and were certainly using it before about 3rd century CE. So this is the earliest recorded usage of a circle character as number 0. The ancient Hindu symbol of a circle with a dot in the middle, known as Bendu or Bendhu, symbolizing the void and the negation, of the self was probably instrumental in the use of a circle as a representation of the concept of zero. The earliest recorded usage of a circle character for the number zero is usually attributed to the 9th century engraving in a temple of Gwalior in central India. Magupta also established rules for dealing with negative numbers and pointed out that quadratic equations could in theory have two possible solutions. So as you can see in the picture, this is Brahmagupta, the mathematician and astronomer. He even attempted to write down these rather abstract concepts, using the initials of the name of colors to represent unknowns in his equations, one of the earliest intimations of what we know known now as algebra. The so-called golden age of Indian mathematics can be said to extend from the 5th to 12th centuries. It seems that India's contributions to mathematics have not been given due acknowledgement until very recently in modern history. So this is the infinity as the reciprocal of zero. Bhaskara II, who lived in the 12th century, was one of the most accomplished of all India's great mathematicians. He is credited with explaining the previously misunderstood operation of division by zero. However, Bhaskara II also made important contributions to many different areas of mathematics, from solution of quadratic, cubic, and quadratic equations, including negative and irrational solutions to solutions to Diophantine equations of the second order to preliminary concepts of infinitesimal calculus and mathematical analysis to spherical trigonometry and other aspects of trigonometry. The Kerala School of Astronomy and Mathematics was founded in the late 14th century by Madhava of Sunga Magrama. So as you can see in the picture, this is Madhava, called the greatest mathematician astronomer of medieval India. He developed infinite series approximations for a range of trigonometric functions including pi, sine, and etc. And that's all my report. Thank you for watching and listening. God bless!